All right, this is CS50, and this is week 3 already, wherein we'll take a look back actually at week 0, where we first began. And in week 0, recall that everything was very intuitive in a sense. We talked not just about representation of information, but algorithms. And we talked about tearing a phone book again and again, and that somehow got us to a better solution. But today we'll try to start formalizing some of those ideas and capturing some of those same ideas, not in pseudocode just yet, but in actual code as well. But we'll also consider the efficiency of those algorithms, like just how well designed our algorithms actually are. And if you recall, when we did the phone book example, wherein I first had an algorithm searching 1 page at a time, and then second went 2 pages at a time, and then third started tearing the thing in half, recall that we, with a wave of the hand, kind of analyzed it as follows. We proposed that if the x-axis here is the size of the problem, like number of pages in a phone book, and the y-axis is the time required to solve the problem in seconds, minutes, page tears, whatever your unit of measure is, recall that the first algorithm was this straight line, such that if you had n pages in the phone book, it might have this slope of n. And there's this one-to-one relationship between pages and tears. 2 pages at a time, of course, was twice as fast, but still really the same shape. The yellow line here indicating that, yeah, it's n over 2, maybe plus 1 if you have to double back, as we discussed. But it's really still fundamentally the same algorithm, 1 or 2 pages at a time. But the third algorithm, recall, was this one here in green, where we called it logarithmic in terms of how fast or how slow it was. And indeed, the implication of this algorithm was that we could even double the size of the phone book, and no big deal, 1 additional page tear, and we take yet another 1,000-page byte out of the phone book. So today, we'll revisit some of these ideas, formalize them a bit, but also translate some of them ultimately to code. And all of that now is possible because we have this lower level understanding, perhaps, of like what's actually inside of your computer. This, of course, is your computer's RAM or memory. And recall that if we kind of start to abstract this away, your computer's memory is really just a grid of bytes. In fact, we don't have to look at the hardware anymore. And we looked at a grid of bytes like this, whereby each of these bytes could be used to store a char, an int, a long, or even an entire string at that. But let's focus perhaps just on a subset of this, because last week, of course, we emphasized really arrays, storing things in arrays. And that allowed us to start storing entire strings, sequences of characters, and even arrays of integers if we wanted to have multiple ones and not just multiple variables as well. But the catch is that if you look inside of an array in the computer's memory, and for instance, suppose these integers here are stored, it's pretty easy for us humans to glance at this and immediately find the number 50. You sort of have this bird's eye view from where you're seated of everything on the screen, and so it's pretty obvious how you get to the number 50. But in the world of computers, of course, it turns out that this is hardware, and computers, for today's purposes, can only do one thing at a time. They can't just take it all in and find instantly some number like 50. So perhaps a decent metaphor is to consider the array of memory inside of your computer really as a sequence of closed doors. And if the computer wants to find some value in an array, it has to do the digital equivalent of opening each of these doors one at a time. Now, how can code do that? Well, of course, we introduced indices or indexes last week, whereby we, by convention, call the first element of an array location 0, the second location 1, the third location 2, and so forth, so-called 0 indexed. And this allowed us to now bridge this conceptual world of like what's going on in memory with actual code, because now we had this square bracket syntax via which we could go searching for something if we so choose. And it turns out if I now paint these red instead of yellow, it would seem that we actually have a pretty good physical metaphor here standing in place for what would be a computer's array of memory if, for instance, you're storing some 7 numbers like that. And so today we begin with a look of a specific type of algorithm. That is for searching. Like searching is all over the place. All of us have probably gone to google.com or some equivalent like already multiple times per day. And getting back answers fast is what companies like Google are really good at. So how are they doing that? How are they storing information in computers' memory? Well, let's consider what this really is. It's really just a problem, as it was back in week 0. The input, though, to the problem for now might be this array of 7 lockers. So that's the input to the problem, inside of which is a number. And maybe for simplicity now, we just want a yes, no, a true, false answer, a bool, that is to say, of whether or not some number, like 50, is in that array. It's not quite as fancy as Google. That doesn't just tell you, yes, we have search results. It actually gives you the search results. But for now, we'll keep it simple and just output as part of this problem, yes or no, true or false. We have found the number we're looking for given an input like that array. But it turns out, inside of this black box that we keep coming back to, there's all sorts of possible algorithms. And we talked about this at a high level conceptually in week 0 with the phone book. But today, let's consider it a little more concretely by way of a game that some of you might have grown up with, namely Monopoly. And so behind these doors, it turns out, will be hidden some denominations of Monopoly money. But for this, we now have 2 volunteers, if you'd like to greet the world.
Hi, I'm Jackson.
Hi, my name is Stephanie.
And do you want to say a little something about yourselves, years, house, dorm?
I'm a first year living in Matthews.
Nice.
And I'm a first year in Canada.
Nice. Well, welcome to our 2 volunteers. So why don't we do this? Would one of you like to volunteer the other to go first?
I'll go first.
OK. All right, so Stephanie's up first, and behind one of these doors here, we've hidden the Monopoly Money 50. And so we'd like you to find the 50. We'll tell you nothing more about the lockers, but we would like you to execute a certain algorithm. And in fact, I'm going to give you some pseudocode for this, and I'm going to give you the name for it. It's called linear search. And as the name implies, you're pretty much going to end up walking in sort of a straight line. But how are you going to do this? Well, let me propose that in a moment, your first step will be to think kind of like a loop for each door from left to right. What do we want you to do on each iteration? Well, if 50 is behind that door, then we want to go ahead and have you return true and sort of hold up the 50 proudly, if you will, for the group. Otherwise, if you get through that whole loop and you haven't found the number 50, you can just throw up your hands in disappointment. False. You've not found the number 50. So to be clear, step 1 is going to be for each door from left to right. How would you like to begin? Yep. Oh, and then, yep, there we go. Yep. Oh. And if you'd like to at least tell, oh, good acting here. What have you found instead?
It's not 50, but 20.
Oh, OK. So step 1 was a fail. So let's move on to step 2. Inside of this loop, what are you going to do next?
I'm going to move to the next door.
OK.
Almost.
Oh, OK, almost, sort of. A 500 instead. Next locker.
I would rather take. No.
OK, we're not telling the audience?
Was a 10.
OK. So keep going. This is step 3 now.
Oh, man.
5, OK. A few more lockers to check.
A little sad, guys.
All right, second to last step.
This one,
No.
kind of close.
All right. And finally, the last step. Clearly, you've been perhaps set up here.
Let's go.
All right. So the number 50. And Stephanie, if I may, let me ask you a question here. So on the screen, this is the pseudocode you just executed. Suppose, though, I had done what many of us have gotten to the habit of doing when you have a if condition. You often have an else branch as well. Suppose that I had done this now. And I'm marking it in red to be clear this is wrong. But what would have been bad about this code using an if and an else, might you say? Any instincts?
Then you would end up like canceling the code before you found the 50.
Yeah, exactly.
And we'd just be eternally sad.
Indeed, when Stephanie had opened the first locker, she had found 20. 20, of course, is not 50. She would have decreed false. But of course, she hadn't checked all of the rest of the lockers. So that would seem to be a key detail that with this implementation of the pseudocode, we actually do go through as we did and only return false, not even with an else, but just at the end of the loop, such that we only reach that line if we don't return truer earlier than that. Well, let's go ahead and do this. Let me take the mic from you if you'd like to take a seat next to Jackson. Jackson, in just a moment, we'll have you come up. Carter, if you don't mind reorganizing the lockers for us. But in the meantime, let me point out how we might now translate that same idea to code. Pretty high level, pretty English-oriented with that pseudocode. But really now, as of last week, we have syntax via which Stephanie and soon Jackson could treat this locker, this set of lockers, as really indeed an array using bracket notation. So we can now get a little closer in our pseudocode to actual code. And the way a computer scientist, for instance, would translate fairly high high-level English, pseudocode like this, to something that's a little closer to C, or any language that supports arrays, would be a little more cryptically like this. But you'll see more of this syntax in the coming days. For I from 0 to n minus 1. This is still pseudocode, but that's kind of like the English-like way of expressing what we've come to know as a for loop. If 50 is behind doors bracket I, so I'm assuming for the sake of discussion that doors now is the name of my variable, this array of 7 doors. But then the rest of the logic, the rest of the pseudocode really is the same way. And so you'll find in time that programmers, computer scientists more generally, when you start expressing ideas, algorithms to someone else, instead of maybe operating at this level here, you now have in your vocabulary really a new syntax that you can be a little more specific, not getting so into the weeds of writing actual C code, but at least now doing something that's a little closer to manipulating an array like this. So Jackson, would you like to stand on up? All right. Yes, yes, support for Jackson here too. Nice. And here now, I'm going to allow you an assumption that Stephanie did not have. Stephanie clearly was really doing her best, searching from left to right, using linear searches, we'll now call it. But they were pretty much in random order, right? There was a 20 over there, there was a 1 over there, and then a 50. So we deliberately jumbled things up and did not sort the numbers for her. But Carter kindly has just come up to give you a leg up, Jackson, by sorting the numbers in advance. And we'd like you this time, much like in week 0, to do something again and again, but this time using what we'll now call binary search. It's exactly the same algorithm conceptually as we did in week 0, but if we translate it to the context of this array, we might say something like this. The first step for Jackson might be to ask the question. If 50 is behind the middle door, where presumably he's done some mental math to figure out what the middle is, then he's going to just return true. And hopefully we'll get lucky and 50 will be right there. Of course, there's 2 other possibilities at least, which would be what? 50 is with respect to these doors? Yeah, so to the left or to the right, alternatively. So if 50 is less than the middle door, then presumably Jackson's going to want to go left. Else, if 50 is greater than the middle door, he's going to want to go right, much like I did physically last week with the phone book, dividing and conquering left to right. But there's actually a 4th case. Let's put it on the board first. What else might happen here that Jackson should consider? Yeah. It's not there. So let me actually go back and amend my pseudocode here and just say, Jackson, if we don't hand you any doors at all, or eventually, as he's dividing and conquering, if he's left with no more doors, we have to handle that situation so that the behavior is defined. All right. So with that said, Jackson, do you want to go ahead and find us the number 50 and walk us through verbally what you're doing and finding?
All right, so it looks like this one is the middle door. So I'm going to open it. But it's 20, not 50.
Oh.
Sad.
OK. What's going through your head now?
So now I'm looking, because 50 is higher than 20, I want to look to the right.
Good.
And look for the new middle door, which would be here.
Nice.
And it's 100.
Oh.
Sad. But 50 is less than 100. So now we know to look left, which would be here. And ta-da!
Nice. Very well done this time around, too. So thank you first to our volunteers here. And in fact, since you're a fan of Monopoly, as we're so informed, we have the Cambridge edition of Monopoly with all your Harvard favorites. Here you go.
Thank you.
Thank you to our volunteers for finding us 50. So that was more popular than we expected. So here we can translate this one more time into something a little closer to code. And again, still pseudocode, but here now might be another formulation of exactly what Jackson just did, just using the nomenclature now of arrays, where you can be a little more precise with your instructions and still leave it to someone else to translate this finally to code. But here we have same question at the beginning. If no doors left, return false. If 50 is behind doors bracket middle. So I'm assuming here, because this is pseudocode, that somewhere I've done the mental math or the actual math to figure out what the index of middle is. For instance, if these are 7 doors in an array, this would be location 0, 1, 2, 3, 4, 5, 6. So somehow I've taken the total number of doors, 7, divided by 2 to find the middle. That's 3.5. We have to deal with rounding, but suffice it to say there's a well-defined formula for finding the middle index given the total number of lockers, divide by 2, and then round accordingly. So that's presumably what Jackson did just by counting or in his head to find us door number 3. Not the third door, the fourth door, but door bracket 3. So this is just saying if 50 is behind doors bracket middle, return true. That was not the case. He found a $20 bill instead. Else, if 50 is less than the doors bracket middle, go ahead, and now it gets interesting. Search doors 0 through doors middle minus 1. So it's getting a little more into the weeds now. But if middle is 3, this one here, well, we want to now have Jackson search if 50 had been, if the number had been less, we want to start at bracket 0 and go up through this one. When we deliberately subtract 1, because what's the point of looking in the same locker again? We might as well do 0 through middle minus 1. Else if 50 is greater than doors bracket middle, which it was, what did we then do? Jackson intuitively searched for doors middle plus 1 through doors n minus 1. And honestly, it gets a little annoying having the pluses and the minuses here, but just think of what it means. This is the middle door. And Jackson then did proceed to search through doors middle plus 1, because there's no point in searching this one again. And then the last element in any array of size n, where n is just our go-to number for the size, is always going to be n minus 1. It's not going to be n. It's going to be n minus 1 because we always start counting arrays at 0. So here then we have a translation into pseudocode that's a little closer to C of this exact same idea. And here we come full circle to week 0. Like in week 0, it's pretty intuitive to imagine dividing and conquering a problem like this. But if you now think back to actually your iPhone, your Android phone, or the like, when you're doing autocomplete and searching the list, it's possible, if you don't have many friends or family or colleagues in the phone, you know what? Linear search, just checking every name for the person you're searching for, might be perfectly fine. But odds are your phone's being smarter than that, especially if you start to have dozens, hundreds, thousands of people in your contacts over the years. What would be better than linear search? Well, perhaps binary search. But there's an assumption, a requirement, which is what? Why was Jackson ultimately able to find the 50 in just like 3 steps instead of a full 7, like Stephanie? Because the array was sorted. And so this is sort of a teaser for what we'll have to come back to later today. Well, you know, how much effort did it take someone like Carter? How much effort does it take your phone to sort all of those names and numbers in advance? Because maybe it's not actually worth the amount of time. Now, someone like Google probably somehow keeps the database of web pages sorted. You can imagine it being super slow if when you type in cats or something else into google.com, if they searched linearly over their entire data set. Ideally, they're doing something a little smarter than that. So we'll formalize now exactly this kind of analysis. And it's not going to be so much mathy as it still will be intuitive. But we'll introduce you to some jargon, some terminology that most any programmer or computer scientist might use when analyzing their own algorithms. But first, a microphone fix. This is my friend Ian.
Just a little tight. Yeah.
All right, thank you. OK, thank you to Ian. All right, we'll clip that out of the video perhaps. So let's formalize now what this kind of analysis is. So right now I claim binary search better than linear search. But how much better and why exactly? Well, it all comes back to this kind of graph. So this, recall, is how we analyzed the phone book back in week 0. And recall that indeed we had these formulas, rough formulas that describe the running time of those 3 algorithms. 1 page at a time, 2 pages at a time, and then tearing the thing again and again in half. And precisely, if you counted up the number number of pages I was touching or the number of pages I was tearing, it's fair to say that the first algorithm, in the worst case, might have taken n total pages. It didn't, because I was searching for John Harvard at the time, which is somewhat early in the alphabet. But if I were searching for someone with the last name of Z, I would have had to keep going and going, in the worst case, through all n pages. Not as bad for the second algorithm, and that's why we do n divided by 2. And even that's a bit of a white lie, right? It's probably n divided by 2 plus 1 in case I have to double back. But again, I'm sort of doing this more generally to capture the essence of these things. And then we really got into the weeds with like log base 2 of n for that third and final algorithm. And at the time, we claimed anytime you're dividing something in half, odds are there's going to be some kind of logarithm involved. And we'll see that today. But today, we're going to actually start using computer science terminology. And we're going to sort of formalize this imprecision, if you will. We are not going to care generally about exactly how many steps some algorithm takes, because that's not going to be that enlightening, especially if maybe you have a faster computer tomorrow than you did today. It wouldn't really be fair to compare numbers too precisely. We really kind of want to, with a wave of the hand, just get a sense of roughly how slow or how fast an algorithm is. So the notation here is deliberate. That is literally a capital O, often italicized, referred to as big O. And so the first algorithm is in big O of n. The second algorithm is in big O of n divided by 2. The third algorithm is in big O of log base 2 of n. But even that is kind of unnecessary detail. When using big O notation, you really don't care about, we'll see, the smaller ordered terms, right? We're not going to care about the divided by 2. Because you know what? The shape of these algorithms is almost the same. And really, the algorithm itself is sort of fundamentally the same. OK, instead of 1 page at a time, I'm doing 2. But if you throw millions of pages, billions of pages at me, those algorithms are really going to kind of perform the same as n gets really large, goes off toward infinity. And the same is true for logarithms. Even if you're a little rusty, it turns out that whether you do the math with log base 2, log base 3, log base 10, you can just multiply one by the other to really get the same formula. So this is only to say a computer scientist would generally say that the first 2 algorithms are on the order of n steps. The third algorithm is on the order of log n steps. And we don't really care precisely what we mean beyond that. And this big O notation, as we'll see, and actually let me zoom out. If you can imagine suddenly making the x-axis much longer, so more pages on the screen at once, it is indeed going to be the shapes of these curves that matter. Because imagine in your mind's eye, as you zoom out, zoom out, zoom out, zoom out, and as n gets much, much, much bigger on the x-axis, the red and the yellow line are essentially going to look the same once n is sufficiently large. But the green line is never going to look the same. It's going to be a fundamentally different shape. And so that's the intuition of big O, to get a sense of these rates of performance like this. So here then is big O. Here is perhaps a cheat sheet of like the common formulas that a computer scientist, certainly in an introductory context, might use when analyzing algorithms. And let's consider for a moment which of our first 2 algorithms, linear search and binary search, fall into these categories. So I've ordered them from sort of slowest to fastest. So order of n squared. It's not something we've actually seen yet, but it tends to be slow because it's quadratic. You're doing n times n. That's got to add up to a lot of steps. Better today is going to be n log n. Even better is going to be n. Even better than that is log n. And best is so-called order of 1, like 1 step, or maybe 2 steps, maybe even 1,000 steps, but a fixed, finite number of steps that never changes no matter how big n is. So given this chart, just to be clear, linear search, let's consider the worst case. In the worst case, how many steps did it take someone like Stephanie to find the solution to the problem, assuming not 7 doors, but n doors? Yeah. So on the order of n. And in this case, it's exactly n. But you know what? Maybe it's arguably 2n, right? Because it took Stephanie a couple of steps. Like she had to lift the latch. She had to open the door. Maybe it's 3 steps. She had to show the money. So now it's 3n, 2n. But there, we don't really care about that level of precision. We really just care about the fundamental number of operations. So we'll say yes on the order of n. So that might be an upper bound, we'll call this, for linear search. And how about binary search? In Jackson's case, or in general, me in week 0, if there's n doors, how many steps did it take Jackson or me using binary search? In this case, it was literally 3, but that's not a formula. Yeah, so it's on the order of log n. And indeed, if there's 7 doors, well, that's almost 8 if you just do a little bit of rounding. And indeed, if you take log base 2 of 8, OK, so that does actually give us 3. So the math actually checks out. And if you're not comfortable with logarithms, no big deal. Just think about it intuitively. Logarithm of base 2 is just dividing something again and again. So on this chart, when we consider big O, which to be clear allows you to describe the order of an algorithm's running time, like the magnitude of it, but it also describes more specifically an upper bound. So in the worst case, for instance, these are pretty good measures of how good, or rather of how bad linear search and binary search might be. Why? Well, suppose you're searching a 1,000-page phone book and the person's name starts with Z. The algorithm's still going to be on the order of n steps. Why? Because it might take you as many as all n steps to find it. Now, that's not necessarily going to be the case in practice. If I use big O as an upper bound, well, it would be nice if there's sort of a corresponding lower bound, especially if you want to consider not just worst cases, but maybe best cases. So what might we use here? Well, so this is a capital Greek omega symbol. So omega is the symbol that a computer scientist uses generally to describe a lower bound on an algorithm, often in the context of best case, though not necessarily. So a lower bound means how few steps might an algorithm take. And here too, same formulas, and we'll fill in these blanks over time. Some algorithms might always take a minimum of n squared steps, or on the order of n steps. Some might only take n log n, or log n, or 1. So something like linear search. When Stephanie started with linear search, she didn't get lucky this time on stage, but what if she had and the first door she opened were 50? How might you then describe the lower bound on linear search in this so-called best case using this list of possible answers? Yeah. Yeah, so omega of 1. So in the best case, the lower bound on how many steps it might take linear search to find something might just be 1 step. Why? Because maybe Stephanie had gotten lucky and we had pre-filled these lockers with the numbers in some other order such that she might have opened the first locker and voila, the number 50 could have been there. So a lower bound arguably could indeed be omega of 1 for linear search. And how about now for Jackson? He used binary search, so he dived right into the middle of the problem. But what would be a lower bound on binary search using this logic? Yeah. Yeah, so again, omega of 1. Why? Because maybe he just gets lucky. And indeed, right in the middle of the lockers could have been the number 50. It wasn't. And so more germane in Jackson's actual practice would have been the big O discussion. But big O and omega, upper bound and lower bound, just allow a computer scientist to kind of wrestle with what could happen maybe in the worst case, what can happen in the best case, and you can even get even more precise, like the average case or the like. And this is indeed what engineers might do at a whiteboard in a company, in a university, when designing an algorithm and trying to make arguments as to like why their algorithm is better than someone else's by way of these kinds of analyses. And just so you've seen it, it turns out that if some algorithm happens to have an identical upper bound and lower bound, you can actually use a capital Greek theta as well. And this is the last of the Greek symbols today. But a Greek theta indicates a coincidence of both upper bound and lower bound. That is, they are one and the same. That was not the case for our discussion a second ago of linear search, not the case for binary search, but you could use the same kinds of formulas if it turns out that your upper bound and lower bound are the same. So for instance, if I were to count everyone, like literally in this room, 1, 2, 3, 4, 5, 6, and so forth, you could actually say that counting in that way is in theta of n, right? Because in the best case, it's going to take me n points at the people in the audience. In the worst case, it's going to take me n. It's always going to take me n steps if I want to count everyone in the room. You can't really do better than that unless you skip people. So that would be an example off the cuff of something where theta is instead germane. Are any questions now on big O, on omega, or theta, which are now just more formal tools in the toolkit for talking about the design of our algorithms? Any questions? No? Seeing none? Yeah, oh, is this yes? No? OK, so we're good. So let's go ahead and translate this perhaps to some actual code. Let me go over to VS Code here, and let's see if we can't now translate some of these ideas to some actual code, not so much using new syntax yet. We're going to still operate in this world of arrays like last week. So let me go ahead and create a program called Search.c by executing code space Search.c in my terminal. And then up here, let's go ahead and include our usual. So include CS50.h so I can get some input. Include standard.io.h so I can print some output. We'll do int main void, which the meaning of which we did start to tease apart last week. The fact that it's void again today just means no command line arguments. And let me go ahead and do this. Let me go ahead and declare, just for discussion's sake, a static array, like an array that never changes. And the syntax for this is going to be give me an array called numbers using the square bracket notation. And I'm going to immediately initialize it to 20, 500, 10, 5, 100, 1, and 50, reminiscent of those same denominations as before. So this is a slightly new syntax that we've perhaps not seen. And the curly braces here, which are different from for loops and while loops and functions, just tell the compiler, please give me an array of whatever size this is containing those numbers left to right. I could alternatively use last week's syntax of saying something like this. Let's see, 1, 2, 3, 4, 5, 6, 7 denominations. I could alternatively do this. And then I could say numbers bracket 0 equals 20, numbers bracket 1 equals 500. And I could do this 5 more times. That's just a little tedious. If you know the numbers in advance, you don't have to tell the compiler how many there are. You can just let it figure it out that your numbers will be 20, 500, 10, 5, 100, 1, and 50. So this is how you statically define an array. All right, let me just go ahead and ask the user now for a number. We'll call it n by using getInt and prompting them for a number. So nothing new there. And now let me go ahead and implement linear search. And the pseudocode we had for this before used some array-like notation. Let me go ahead then and start similarly. For int I, and you almost always start counting at I by convention, so that's perhaps a good starting point. I'm going to do this so long as I is less than 7. Not the best design to hard code the 7, but this is just for demonstration's sake for now, because I know how many numbers I put in there. And then I'm going to do I++. So now I have the beginnings of a loop that will just allow me to iterate over the entire array. And let me ask this. If the current number at location I equals n, which is the number the human typed in, then let's go ahead and do something simple like printf, quote unquote, found, \n. And then, per our discussion last week, to indicate that this is successful, I'm going to return 0 if I found it. And if I don't find it, I'm just going to go down here and by default say not found, \n. And just for convention, just for good measure, per convention, I'll return 1, or really any value other than 0. 0, recall, means success, and any other integer tends to mean error of some sort, irrespective of the number I'm looking for. So just to revisit, the only thing that's new here is this syntax for creating an array of 7 numbers, these numbers. And then after that, we have really highlighted here an implementation of linear search. I mean, this is the C version, I dare say, of what Stephanie did on the board, whereas now the array is called numbers instead of doors. But I think it's pretty much the same. Let me go ahead and open my terminal window and run make search. Seems to compile OK, /search. And let's go ahead and search for a number. We'll start with what we did before, 50. And it's found. Let's go ahead and run it again, /search. Let's search for maybe 20 at the beginning. That one, too, is found. Let's run it one more time, searching for like 1,000, which is not among the denominations. And that one, indeed, is not found. So we've taken an idea from week 0, now formalized in week 3, and just translated it now to code. Questions on this implementation of linear search? Linear search. Nothing. Oh. So successful so far today. OK, so let's see if we can't maybe make this a little more interesting and see if we can't trip over a detail that's going to be important in C. Instead of doing numbers, let me go ahead and do this. We'll stay on theme with Monopoly. And I went down the rabbit hole of reading the Wikipedia article on Monopoly and the original pieces or tokens that came with Monopoly. And it turns out we can represent those with strings. So I'm going to create an array called strings, plural, of whatever size I defined here. And the very first Monopoly pieces back in the day were a battleship that you could play with, a boot, a cannon, an iron, a thimble, and a top hat, some of which you might know from the game nowadays. Turns out they've been changing these, had no idea, over the years. So here is now an array of strings. Let me go ahead and prompt the user now, not for an integer anymore. I want to now search for one of these strings, still using linear search. So let me create a string s, set it equal to getString, prompt the user for a string to search for. And then I think my code here is almost the same, except for one detail. I now have an array called strings. I now have a variable called s. But it turns out, for reasons we'll explore in more detail next week, this line of code is not going to work. And it turns out the reason has to do with what we discussed last week of like what a string really is. And what is a string again? A string is an array. And it turns out, though, that equals equals is not going to generously compare all of the characters in an array for you just because you use equal equals. It turns out it's not going to compare every letter. And so thankfully, there is in the string library that we introduced last week a solution to this problem. The reason for the problem we'll explore in more detail next week. But for now, just know that when you want to compare strings in C, especially if you've come into the class knowing a bit of Java or Python or some other language, you cannot use equals equals. Even though you could in Scratch, you cannot in C. So what I have to actually do here is this. I have to ask the question, does the return value of a function called strCompare or strcomp equal 0 when passed in the current string and that user input? So if you read the documentation for this function called strCompare, you'll see that it takes two strings as input, first one and second one. It then, someone decades ago wrote the code that probably uses a for loop or a while loop to compare every character in each of those strings. And it turns out it returns 0 if they are in fact equal. Turns out, too, it will return a positive number or a negative number in other situations. Any intuition for why it might actually be useful to have a function that allows you to check if two strings are equal? If they're not equal, what else might be interesting to know when comparing two strings? Or if certain values are? OK, possibly. Maybe you want to know just how similar they are. And that's indeed an algorithm unto itself. But strCompare is a little simpler than that. Exactly. If you're trying to like alphabetize a whole list of strings, just like your phone probably is for your contacts or address book, it turns out that strCompare will actually return a positive number or a negative number or a 0 based on whether maybe it comes alphabetically first or later or in fact equal. So that can be a useful thing. And that's just a teaser for a lower level explanation that we'll see next week. So now let me cross my fingers and see if I got this right. Let me go ahead and do make search. Did compile, OK, albeit slowly, /search. And let's search for something like the thimble. And we see that that's indeed found. Otherwise, let's search for something that I know isn't there, like a race car, which was there when I grew up. But, segmentation fault, core dumped. And actually, some of you have tripped over this error before. Anyone want to admit seeing this? So yeah, not something we've talked about. And honestly, not something I intended just now. But that, too, we'll see next week. Any intuition for why my program just broke? I didn't really change the logic. It's still linear search. Let me hide the terminal so you can see all of the code at once. The only thing I did was switch from integers to strings. And I switched to strCompare here. But segmentation fault happened. And the teaser is that that somehow relates to the computer's memory. Yeah? Yeah, and this is subtle, but spot on. So 1, 2, 3, 4, 5, 6 elements total in this array versus the 7 numbers of monopoly denominations that we had earlier. And this is where, see, sort of case in point, this came back to bite me. The fact that I hard-coded this value as opposed to maybe separating it out as a constant or declaring it higher up kind of bit me here, because now I'm iterating over an array of size 6. But clearly, I'm going one step too far, because I'm literally going to iterate 7 times, not 6. So it's as though I'm looking at memory that's over here. And indeed, next week, we'll focus on memory. And that's just a bad thing. So odds are, not even seeing your code from this past week, if any of you have had segmentation faults, odds are you touched memory that you shouldn't have. You maybe looped too many times. You might have used a negative number to get into your array. In general, you touched memory that you shouldn't have. And you touched a segment of memory that you shouldn't have. The fix, though, at least in my case, is simple. Just don't do that. So let me go ahead and recompile this. Make search. /search, and I'll search again for race car, enter, and now it does not crash, but it does tell me it's not found. So subtle, but something you might yourself have tripped over already. Questions then on what I just did, intentionally or otherwise? Yeah, in front.
One thing is, the program still works if you don't do return 0, return 1. So what is the purpose of doing that?
A really good question. So the program will still work even if I don't return 0 or return 1. In fact, let me go ahead and do that and just hide my terminal window for a second. Let's get rid of the return here. Let's get rid of the return here. However, watch what happens here. Let me go ahead and recompile this, make search. Let me scroll up in my code here. Let me go ahead and do /search. And let me go ahead and search for the first thing in the list, battleship. So I know that this should be found. I hit enter. Huh, interesting. So it's saying found, not found. But do you see why logically in this case? Exactly. So the loop is still running. So there's a couple of solutions to this. I could, for instance, somehow break out of the code here, but that's going to still result in line 18 executing. I could then instead just return here. I don't strictly need to return 1 down at the bottom, but I made this claim last week that it tends to be helpful as your programs get more sophisticated to at least signify, just like a real world programmer, error codes when something goes wrong. So returning 0 in main is the easiest way to signify my code is done. I'm ready to exit successfully. That's it. But down here, I could absolutely still return 0, because it's not a huge deal. It's not really an error that deserves annoying the user with some kind of pop-up that something went wrong. But return 1 is just a lower level way of signaling, it didn't really find what I was looking for. And remember from last week, you can see this as follows. If I recompile this again, now that I've reverted those changes, so make search, and if I do /search and search for battleship, which is indeed found, recall I can execute this magical command echo $? Which you're not going to often execute, but it shows you what main returned. If I run search again and search for race car, which is not found, I see not found, but I can also run this command again and see that, oh, it returned 1. So now if you fast forward a few months, a few years, when you're actually writing code in a company or for larger projects, you might want to be automating software. You might not want the human to necessarily be running it manually. You might want code to be automated by some nightly process or something like that. Using these exit codes, can a program determine yes or no that other code succeeded or failed? Other questions on linear search in this way? No? All right, well, let's translate this to one other feature of C here by incorporating these two ideas now into one other program. So I'm going to create a phone book in C by doing code space phonebook.c. And let's combine some of these ideas and implement this notion of like searching a phone book for an actual name and getting back a number. So I'm going to go ahead and quickly include some of the same things, CS50.h so we can get input, standard IO.h so we can print output, and I'm going to preemptively include string.h in case we need that one as well. Int main void, no need for command line arguments today. And let me give myself now an array of names for this phone book. So string names equals, and then in curly braces, how about Carter will be one person in the phone book, and David, myself, will be the other. So we'll keep it short so we don't have to type too many names. But this is a phone book with 2 people thus far. Suppose now we want to also store Carter's phone number in mine. So it's not just saying found or not found. It's literally looking up our phone numbers like a proper phone book. Well, at the moment, there's really no way to do this. I could do something hackish, like I could put a number like 617-495-1000 after Carter. I could maybe do something like 949-468-2750 after me. But now you're kind of doing the whole apples and oranges thing, right? Like now it's not strings. It's a string int, string int. All right, so maybe I could just make all of these strings. But now it's just a conceptual mixing of apples and oranges. Like, yes, that's an array of 4 strings. But now you're on the honor system to know that the first string is a name, the second string is a number, the third string is, like, you can do it, but it's a bit of a hack, so to speak. So what might be cleaner than this? Instead of combining our phone numbers into the same array as our names, what else might we do that's perhaps a little better? Say a little louder. A 2D array, possibly something we could do. I'm going to keep it even simpler now because we haven't used those by name, even though that is, we saw last week, technically what argv is. What else could I do if I want to store names and numbers? Yeah. Yeah, let me go with this suggestion. Just it's a little simpler. Rather than complicate things in literally different dimensions, let me go ahead and do string. Well, I could do int numbers, but you know what? So that we can support punctuation like dashes or even parentheses or country codes, I'm going to do this instead. I'm going to do string numbers so that I can represent Carter's number as quote unquote +1 for the US, 617, 495, 1000, complete with hyphens, as is US convention. And then for mine, I'll go ahead and do +1, 949, how about 468, 2750. Semicolon. And now down below, let's actually enable the user to search this phone book, just like in week 0 we did. String name equals get string, and let's ask the user for a name, presumably David or Carter or someone else. And now let's re-implement linear search. So for int I gets 0, I is less than 2, and do as I say, not as I do. I think we should beware this hard coding, but we'll keep it simple for now. I++, and then in this for loop, I think we have all of the ingredients to solve this. So if the return value of stir compare of all of the names, bracket I, comparing against the name that the human typed in, if all of that equals 0, that is, all of the characters in those 2 strings are equal, then I think we can go ahead and say found, just like last time. But you know what? Let's actually print Carter's or my phone number. So found %s, and we'll plug in numbers, bracket I. And then just for consistency, I'll return 0 here. And down here, how about I'll say something like printf not found, just to be clear. And then I'll return 1 as well. So just to recap, here's all of the code. It's almost the same as before, except now it's useful. I'm not just saying found or not found. I found a number in Monopoly, or I found a piece in Monopoly. I'm looking up in one array, one of the strings, and then I'm printing from the other array the answer. So let me go ahead here and run the compiler, make phone book, enter. OK, that's promising. No errors. /phonebook now. And let's search for instance, Carter. Enter. All right, so we found Carter's number. All right, let me do that again. Phone book. Let's search for David. All right, we seem to have found David's number. All right, let's do it one last time. Phone book. Enter. And now we'll search for like John Harvard. Enter. Not found. All right, so I dare say, albeit with minimal testing, this code is correct. Would anyone now like to critique the design? Does something rub you the wrong way, perhaps, about this approach here? And as always, think about how, if the program maybe gets longer, more complicated, how decisions like this might unfold. Yeah? OK, so if I is less than 2, so technically, if I change the number of people in this phone book, I'm going to have to update I. And we've already seen that I get myself into trouble. So that's bad design. Good. Yeah, so again, I'm sort of trusting myself not to screw up. If I add John or anyone else to the first array, but I forget to add their number to the second array, you know, eventually things are going to drift and be inconsistent, and then the code will be incorrect at that point. So sort of a poor design setting me up for future failure, if you will. Other thoughts? Yeah. Yeah, really good. We're assuming the same order. From left to right, the names go, and from left to right, the numbers go. But that's kind of just the honor system. Like, there's literally nothing in code preventing me from reversing the order for whatever reason, or maybe sorting the names. Like, they're sorted now, and maybe that's deliberate, but maybe it's not. So this honor system here, too, is just not good, right? I could put a comment in here to remind myself, to, note to self, always update arrays the same way. But like, that's something's going to happen eventually, especially when we have not 2, but 3, but 30, 300 names and numbers. It would be nice to keep all of the related data together.